Hi students, welcome to Vedantu J English. I'm Diksha, your chemistry master teacher. So everyone, let me know in the comment section if I'm clearly visible and audible to you. Yes. So today, like we did yesterday, organic reactions, naming reactions, important reagents, and some part of GOC also I taught you. So today we are going to do inorganic exception. Like same way we are going to do that. It will be a fast track revision. Okay, so everybody, you just need to tight your seat belts and sit here because this is going to be a roller coaster ride. Okay, inorganic exceptions is not a simple thing, right? I know so many things, but the problem is, ma'am, what we need to remember, what we not need to need to remember. But one thing I'll clarify: it's not like you will only watch this lecture and you will be like, I'm good for inorganic chemistry. No. Okay. So one thing very important is that if you're talking about inorganic exception, just by watching this lecture, you will not be able to remember this. But yes, after this, I'll provide you with the notes in the description box. You have to go through the notes as well on your own. Right? Only then that thing will retain in your head. Otherwise, this lecture will teach you how to understand these things, what are the things you need to remember. But again, you will need at least 2 time division before your exam. So are you all ready for that? Yes, everybody. Are you all ready for that or not? Okay, so shall I start? Shall I start? Shall I start it? Shall I start the lecture? Yes. Now let us start it without wasting any time. So starting with the first thing here, that is coordination chemistry exception. So what are the exceptions in the coordination chemistry? Let us talk about that. First is, if CO3 positive is bonded with H2O and oxalate, then ligand act as strong field ligand. Okay. If CO3 positive is attached with H2O, which is a weak field ligand, and oxalate, then these two weak field ligand will act as strong field ligand. That is a very important exception. Next is, if CO positive is bonded with H2O, then ligand act as a strong field ligand. Even with water, if you have CO2 positive, even then water, which is a weak field ligand, will act as a strong field ligand. Next is, if Ni4 positive is bonded with fluoride ion, then ligand act as a strong field ligand. Very important. That usually fluorine is a weak field ligand, but only in case of when it is bonded to Ni4 positive, then it will act as a strong field ligand, right? Next is, Fe2 positive and Mn2 positive are bonded with NH3, then ligand act as a weak field ligand. Now, beta, NH3 is a strong field ligand, but when it is bonded to Fe2 positive or Mn2 positive, it will act as a weak field ligand. Okay, so that is also exception. Next is 3D series element in +2 oxidation state. 3D series like Saktiv, Karman, Fico-Nico-Jan, all these in +2 oxidation state form outer octahedral complexes up to NH3 in the spectrochemical series. Directly you can remember this, that 3D elements, 3D series elements, Saktiv, Karman, Fico-Nico-Jan, in +2 state, they will form outer octahedral. That means they will form sp3d2 geometry hybridization when up to NH3 in the spectrochemical series. Next is compounds of PT-PDAU with coordination number 4 prefers DsP2 hybridization with any type of ligand. Okay, that means if you have compound of PT, PD, AU, they will prefer, rather than sp3, they will prefer square planar, that is DsP2 hybridization. Is this page clear to everyone, beta? These are all the exceptions of coordination chemistry in one page. Notes will be provided to you. You can also take the screenshot here. I'll get the site, right? You can also take the screenshot here. It is very important. Got it? Next we have is trends and exceptions of boron family. Now I'll start with P block. Okay, so coordination chemistry we have done already. Now we will start with the P block, which is going to take a lot of time. So are you all ready for P block or not? Everybody let me know in the comment section. If you guys are ready for P block and you loved coordination chemistry, then hit the like button on this session, and I also want to see green hearts in the comment section if you're ready for P block. I can't see any energy here, right? Tanu, complicated, ready, ready, okay, that is good. Ma'am, duration, that is going to be 1 hour, okay, yes. But I am not going to start. This is not a recorded version, okay? I am not going to start if you are not going to reply. It's very clear in my lecture. You can't come here and take someone for granted who is doing so much hard work for you, right? If you can respond, I would love to teach you. If you have no respect for a teacher, you are like, okay, teacher is standing there for hours and hours, but we are so lazy to type. Yeah? Then I would say that will make the class very dull, right? Okay, yes, chal. Now, let us see the exceptions of P block here. First, we will talk about boron family, that is group number 13. Okay, so this table that we have is from your NCERT. From this table, I have extracted some important points. Let us see those points here. So, first point is atomic radii. Okay, atomic radii follows the simple order that we know that down the group atomic radii increases. So it will be BAL. We know that what is the order? It is BAL, Gaye, Indian, Te. So what you can see that over here, you can see one exception that it should be that aluminium is less than gallium. But in reality, it is opposite. Gallium is less than aluminium, right? So why it is so? Because of the d orbital shielding. Because of the d orbital shielding, we have this exception here, right? Next is ionization enthalpy. Ionization enthalpy, you will see even weird exception here. How you can remember that exception? Okay, how you here in the radii, this is the exception. If you talk about the exception of ionization enthalpy, you can remember this by something like this. That is Bal, Gaye, Indian, Te. Okay. So now when you look at this W, this will be boron. After that you have thallium, boron. After that you have thallium. Then you have gallium. Then you have aluminium. Then you have indium. As you can see, this is your order of ionization enthalpy. This is how you can remember the order of ionization enthalpy, right? Reason, because of 3d orbital, 3d shielding, poor shielding of d orbitals, poor shielding of 4f orbitals, lengthenoid contraction. That is the reason. Next is electronegativity. As you can see, electronegativity also observes a opposite trend. Here you can see boron, then aluminium, then gallium, then indium, then thallium. Right? So that means what should have happened that along the period electronegativity increases, down the group it decreases. So it should have been B, then you have Al, then you have Ga, then you have ion, then you have Tl, right? But it is the opposite order as you can see here, right? Okay, it is the opposite order as you can see here. Oxidation state, general oxidation state is +3 +1 and stability of +1 oxidation state increases down the group due to inert pair effect. Now beta, always remember this, I will teach you in every single group. Every single group you are going to learn this one thing about the oxidation state. And what is that thing? I'm going to write it here. Very, very important thing, that always lower oxidation state, stability of, this is for all the groups, stability of lower oxidation state, it will increases down the group, okay, increases down the group. And if you talk about the oxidation states here, it is always going to be, let's say this is the order, this is NS1, NS2, NP1, that is going to be the electronic configuration. The number of electrons in P will give you the lower oxidation state. The number of electrons in S and P together will give you higher oxidation state. Number of electrons in P is 1, so it is +1. Number of electrons in S and P is 3, so it is +3. Okay, that is how you are going to do that. What is the order? Lower oxidation state, I am going to write lower oxidation state is P, and higher oxidation state will be number of electrons of S and P. These are the something that you should remember to remember all these things, right? Next is metallic character, it increases down the group. Melting point, beta, very important. Here also you can see that what will happen. Boron, aluminium, then thallium, then indium, then you have gallium. Gallium has the lowest melting point, and this question is also very frequently asked. Right? Boiling point, it simply decreases down the group. Density also, it increases down the group. There is no exception. Exception we observed here, here, and here. These are 1, 2, 3, 4 exceptions here. Next is the properties, talking about the reactivity with the air. Okay, so if you talk about the reactivity with the air, how you're going to do the reactions here? React with air to form oxide at moderate temperature and nitride at high temperature. Crystalline boron is unreactive. Okay, amorphous boron reacts. Crystalline boron is unreactive. Aluminium forms oxide layer and does not react further. These are the important points from the reactivity with the air. Okay, these are the important points from the reactivity with the air. Okay, understood? Here also you can see gallium with unusually low melting point could exist in liquid state during summer. As I told you here, these are some of the important lines from your NCERT. This is gallium here. It has unusually very low melting point. So the NCERT line is that it could even exist in liquid state at room temperature. It has high boiling point, makes it a useful material for measuring high temperature. This question is very important. Which of the following you can use to measure the high temperature? That is gallium. Okay, gallium can be used to measure high temperatures. Okay, next is due to small size of boron, the sum of first 3 ionization enthalpy is very high. This prevents it to form +3. This question also has been asked so many times, that why boron does not form +3. B3 positive does not exist. Why? These reasonings are very important for your inorganic chemistry. Why it is so? Because first ionization enthalpy is very high, so that is why B3 positive does not exist, forces it to form only covalent bonds. Okay. Next is reactivity towards air. This is what I was telling you, that this is the important point of NCERT. Now I will tell you that where we have picked up that, right? If you can see here, very, very important, reactivity towards air, right? Boron is unreactive in crystalline form. Unreactive. Aluminium forms very thin oxide layer on the surface which protects the metal from further attack. Okay, very important lines. Amorphous boron and aluminium metal on heating in air forms boron oxides or aluminium oxides respectively. With dinitrogen at high temperature, they form nitrides. This is what I told you, that at low temperature they form oxides, at high temperature they form nitrides, right? The nature of these oxides varies down the group. Boron trioxide, it's very, 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 very important, right? Which is acidic, which is basic. Boron trioxide is acidic and react with basic oxides forming metal borates. Aluminium and gallium oxides are amphoteric beta. This is very important. Boron oxide is acidic, right? Aluminium and gallium oxide is amphoteric. Very, very important. Amphoteric. Those of indium and thallium are basic in nature. Indium and thallium are basic in nature. Basically, down the group, basicity increases, acidity decreases. Okay, so these are the some very, very important oxides. These are boring, but these are going to give you the marks. Okay, so these are going to give you the marks. Very important lines, right? Next is, let me just conclude other parts for boron. See, I am just doing the conclusion. From here, you will see so many questions in your previous year questions as well. Reactivity with acids and alkalis. So boron does not react. Aluminium react with both acids and alkalis to liberate hydrogen gas. Aluminium is passive with concentrated nitric acid, which is a very, very, very strong oxidizing agent. Reactivity with halogens. Reacts with halogens to form trihalides, very simple. But here exception is very important, that except triiodide of thallium, it does not exist. All the other halides exist, but triiodide of thallium does not exist. It's a very, very important point. Next is nature of trioxides that we have seen already. Boron is acidic, aluminum, gallium, amphoteric, indium and thallium is basic in nature. Okay, got it, students? Now next one is the carbon family. So again, from this table, some important generalizations from this table. You should always go through the table. Okay, tables are very important in inorganic chemistry. So what are the important generalizations from this table? First is atomic radii. Atomic radii is Kasi, Gai, San Prabhu. It is following the same order. But ionization enthalpy, you will see a change, right? That is over here, right? That is reversed again because of the poor shielding effect of f orbital, right? Electronegativity, very important. This has been asked in your last year 2023 exam, right? So that was, here you will have carbon, then Pb, then you have silicon, germanium and tin as equal, right? Okay, so you should know only that electronegativity that is given in the this NCERT. You should not follow the electronegativity because the question was, it was basically if some students have taken it from the Google, the chart from the Google and chart from the NCERT, they are different. Okay, so you have to follow this chart. Electronegativity of carbon is 2.5, then it is silicon is 1.8, germanium is 1.8, tin is 1.8, lead is 1.9. That is why you have carbon, then lead, then you have silicon, germanium, then you have tin. Okay, these are equal, that is 1.8. Okay, next is oxidation state. So as I told you, you have NS2NP2. Okay, so lower oxidation state is +2, higher oxidation state is +4. Stability of lower oxidation state will always increase down the group. So +2 increases down the group due to the inert pair effect, right? Metallic character, it will increase down the group. Okay, always it will increase, non-metallic will increase along the period. Next is the melting point decreases up to 10, then increases. If you see this melting point, if you see the melting point, it is decreasing up to 10, then it is increasing. Can you see it is decreasing 4,000, around 1,500, around 1,200, then 500, then again it is slightly increasing to 600. Okay, so all the generalization from the table we already have written here. Next is boiling point, it decreases down the group, there is no exception, but here you can see one exception. Next is density, it always increases down the group. Okay, now next is the properties. So if you talk about the properties, right, firstly let us go through this property, reactivity with air. So what will happen? It reacts with air to form monooxide and dioxides. Okay, so now this is very, very important, that how does it react with air. Let me tell you some very important paragraph directly from your NCERT. Okay, beta, these we have picked directly from NCERT. So you need to see this lecture if you actually want to gain full marks in all these exceptions and block chemistry. Reactivity towards oxygen. All members when heated in oxygen from oxides, there are mainly two types of oxides. One is monooxide, other is dioxide of the formula MO and MO2, right? SiO only exists at high temperature. Silicon oxide will only exist at high temperature. Oxides in higher oxidation state of element are generally more acidic in nature. Remember, when you have acidity, beta, this is a very, very important thing. Acidity is directly proportional to oxidation number. If you have the same metal and if I have two oxides of the same metal, then according to the oxidation number, their acidity will increase, right? Next is the dioxide CO2, SiO2, G. This is a very, very important line, that CO2, SiO2 and GeO2 are acidic, whereas tin oxide and lead oxides are amphoteric in nature. Very, very, very important. As I told you, in boron also it was here. In boron also we did this here. Okay. Boron oxides also we did this here. Wait a minute. Right. Now we are talking about the oxides of carbon. Right. Carbon family. Boron family was this thing. Right. And carbon family is over here. Right. Very, very, very important lines. Okay. Then you have among monoxides, CO is neutral. Beta neutral oxide, so you write it here only. Neutral oxides are CO, NO and N2O and H2O. These are neutral oxides. So you write it here only. These are neutral oxides. GeO is distinctly acidic, whereas tin and lead oxide is amphoteric in nature. Very, very important. Okay? Okay, so all this full paragraph becomes very important because they ask you question from the acidity, basicity of the oxides, which is a very frequently asked question. Okay, next we have is reactivity towards water. With water, what does it make? Only tin reacts with steam. Rest all do not react with water in any form. Only tin will react with the steam. Reactivity with halogens, what we have? Reacts with halogen to form dihalides and tetrahalides. That is very simple. Okay, students. Next is reactivity towards halogen, the full important part of reactivity towards halogen. The central metal in these halides undergo sp3 hybridization. The molecule is tetrahedral. Exceptions are tin fluoride and lead fluoride, which are ionic in nature. This is important. They are covalent in nature, but tin and lead fluorides are ionic in nature. This is very important line. Lead iodide does not exist. Very important line, beta. PbI4 does not exist. Why it does not exist? Because PbI bond initially formed during the reaction does not release enough energy to impair 6s2. Enough energy is not released to impair 6s2 electrons and excite one of them to higher orbital to have 4 unpaired electrons. That means for the chemical bond, you need to excite the electron, you need to have the half-filled orbitals. That does not happen. So that is why PbI4 does not exist. Here you can get assertion reasoning question because these lines are directly from your NCERT. Okay. So wherever you see because, that means easily assertion reasoning question can be formed out of this one. Right. Next you have, this also we have done. Next is covalent radius. So if you talk about the covalent radius, we know that carbon exists as covalent, it forms covalent bonds. So there is a considerable increase in covalent radius from carbon to silicon. Thereafter, from silicon to lead, a small increase in radius is observed. This is due to presence of completely filled DNF orbitals in the heavier metals. As you go down the group, there is D orbital involvement, there is F orbital involvement. That is why the radius will not increase to that much extent. Right, so covalent radius is carbon, silicon, then germanium, then tin, then lead, right? But the increment is going to get decreased after that. But silicon and germanium have almost similar due to the poor shielding effect of D. Tin and lead have almost similar due to poor shielding effect of F orbitals here. Right? Okay? F orbitals here, they have the poor shielding effect. Right? Next is ionization energy. This beta we have already seen that the change was here because of the poor shielding effect of D and F orbitals. Right? Beta always the reason is going to remain the same. D orbital poor shielding effect, F orbital poor shielding effect. Right? That's why I am not focusing on that. The electronegativity values, this also trend we have seen. Okay? Density also we have seen. Next is melting point also beta we have seen. Exceptionally high, right? Next is catenation. This property we have not seen. So catenation is the self-linking property, right? That is maximum in carbon, then silicon, and then it will decrease down the group. Pb has no catenation tendency, right? Okay. Now chemical properties is, since the sum of first 4, very important, first 4 ionization enthalpy is very high, compounds in +4 oxidation state are generally covalent in nature. They are not ionic in nature. Carbon always in when it is forming 4 bonds, so it is forming through covalent nature. It is not forming through ionic nature. Why? Because first 4 ionization enthalpy is very high. That is why it will not lose the electron, but rather it will share the electron and it will form covalent bonds here. Okay. Next we have reactivity towards halogens. Okay, so how does it make with halogens? What are the important exceptions? The central metal atom in these halides undergo sp3 hybridization. Okay, that we know. Molecule is tetrahedral in shape. Exception. Okay, exceptions. Tin fluoride and lead fluoride. That is, I think we have done this before. Is it? Achha, this we have done before, na? This we have done before also. I think we have done this. Here we have done this. Na? So we have already done this. So let me just delete this page because that is a repetition. Okay. So that means we have completed carbon family as well. Okay. We have completed carbon family as well. These are the some important points, exceptional points. Okay. Next is when we talk about nitrogen family. So in nitrogen family, this is the table, but ma'am, table is very confusing, ma'am. What to do? So we have a direct thing for you which you can remember in your exam because this table is very difficult to remember. But these things are easy to remember. Let us see what. So for group 15 element, that is nitrogen family, that is called nitrogen. So here what you have, electronic configuration, we know extra stable electronic configuration due to half filled p orbital, as you can see np3. So that is why it is extra stable. Right now the properties are atomic. First, if you see the atomic and ionic radii, that will increase down the group. Reason is due to increase in the number of inner shell. Ionization enthalpy decreases down the group, electronegativity decreases down the group. That is the general property. Non-metals are nitrogen, phosphorus, arsenic and antimony are metalloids, bismuth and this MC, that is not even in your syllabus because that is the radioactive element, right? So this bismuth is metallic in nature, right? If you see the properties here, this is the table, better version of NCERT. Now from here, let us see what are the different properties that you can see here. Firstly, we will see the, wait a minute. Firstly, I'll talk about ionic radii. Okay? Firstly, I'll talk about the ionic radii. Right? What will happen to the ionic radii? Right? These are the important lines. From AS to BI, bismuth, only a small increase in covalent radius is observed. This is due to presence of completely filled d or f orbital in the heavier member. So I'll just show you this thing here. So basically, if you see this thing here, what is happening to the atomic radius? Okay, this is the radius 70, 110, 121, 141, 148. It is increasing, but what you can see here, that here the gap is very large. Here the gap is also quite decent. But here, as you can see, the gap is decreasing. The gap is very less, right? So what has happened basically, down the group you have heavier elements which has DNF block. That is why the gap has decreased here. But there is no exception as such here, right? Then if we talk about ionization enthalpy, much greater than group 14, very important line. The ionization enthalpy is greater than group 14. Why? Due to half filled orbitals in NP3, right? Because NP3, in the electronic configuration of this group only, you have NS to NP3. You have half filled p orbitals. So that is why there will be greater energy will be required to take out electron from this. That is why the ionization enthalpy are greater than group number 14. As such, there is no exception within the group, but with group number 13, it is greater. When we compare this to group number 14, this is greater. Electronegativity is here, it is decreasing, but in the end, antimony and bismuth, that will become equal to each other, right? Antimony and bismuth will become equal to each other, right? Melting point is first increases from nitrogen to arsenic, then decreases from antimony to bismuth. So this is the order of melting point. Firstly, what it will do? Firstly, it is going to increase, then it is going to decrease from antimony. Okay. So what we are doing here, maximum is for arsenic, then antimony, then bismuth, then phosphorus, then nitrogen. That is the order of melting point for the nitrogen family. Right. Next, we have the boiling point. In general, increase but the melting point increases up to arsenic, then decreases up to bismuth, right? This we have done. Except nitrogen, all other elements will show allotropy, right? Except for nitrogen, nitrogen will not show any allotropic forms, right? Okay. Now let us do the chemical properties. So I'll just show you the chemical properties here also. Okay. This we have done already. Let us see the chemical properties now. If you see the chemical, these are the physical properties now. So this is a table, this is a chart. So I'll just show you, go through that chart first. All the elements in this group are polyatomic in nature. N2, right? P8, P4. All these are polyatomic. Dinitrogen is diatomic gas, while all other are solid. Only nitrogen is a gas. Otherwise, all the other elements are solid in nature, like phosphorus, red phosphorus, white phosphorus. They are solid, right? The boiling point increases from top to bottom. There is no exception, but melting point increases up to arsenic, then decreases up to bismuth. This is the short form of everything, okay? Now, except nitrogen, all show allotropy. Metallic character increases down the group, okay? Metallic character increases down the group. Understood? Yes, everybody? Chal. Now, let us do some important things regarding the hydrides here. Okay, some very important things regarding hydrides. So, everybody see this page on the comment section on the screen. So, if you see reactivity towards hydrogen, they are from hydrides. If they ask questions from hydrides of nitrogen, from nitrogen family, from the hydrides of oxygen family, from the hydrides of halogens. These three are very important topics. Okay, so see this thing. If you talk about the thermal stability, that will increase down the group, right? So napi aise sharab bhai. So this is, it is increasing down the group. Reducing character is decreasing down the group. I'll just write here, it is increasing down the group. This is increasing down the group. Boiling point, if you talk about, that has a variable thing. So what we are supposed to do, down the group it should decrease, down the group it is down the group it is increasing only because the size is increasing. But NH3, because of the hydrogen bonding, okay, that will lie in between them. Okay, hydrogen NH3, because of the hydrogen bonding, it will not have the minimum boiling point. It will strengthen up the boiling point, and hence it is not lying here, rather it is lying here. This is a very, very important question that has been asked so many times. Then there is basic character, that is definitely decreasing down the group. Okay, so what are the things that are decreasing? If you see this, wait a minute, this is decreasing, this is increasing. Na? Ulta I have written. This is decreasing. Okay, this is increasing. So from that, I'm going to write some more things that they can ask you. Instead of reducing character, they can also ask you the acidic character. Okay. Reducing character, acidic character is the same thing, that is going to increase down the group. Basic character is opposite of acidic character, that is why it is decreasing down the group. Thermal stability, or even if you talk about bond dissociation enthalpy, bond dissociation. So if you say that it has the minimum stability, that is why its BDE, bond dissociation energy, is going to be maximum. So bond dissociation enthalpy energy is also going to be maximum down the group. Okay, understood? Because stability is less, that is why, wait a minute, stability should be more than BD. No. This should be the BD. Wait a minute. If you talk about stability, more the stability, more difficult it is to break it. So this has a maximum stability, then it will have the maximum bond dissociation enthalpy. So BDE, that is bond dissociation enthalpy, and thermal stability have the same order. Acidity, reducing character, has the same order. And here basic character also you can add. That is also directly decreasing down the group. Okay, so these are the some important things that they ask you in the exam. Bond dissociation, basic, acidity, reducing power, thermal stability, boiling point also they ask you because of this NH3 here, right? Okay, now next is reactivity towards oxygen. So one by one we are going to see the chemical properties here, that what is happening here. So let us see Reactivity towards oxygen is basically, we are going to talk about oxides here, okay? So, all the elements from two types of oxides, that is E2O3 and E2O, right? So, this should be E2O, because this is showing NS2, NP3, so it is 5 now, so it will be E2O5. Okay, because cross valency element can have either +3 or +5, so it will be E2O5. The oxides in the higher oxidation state are more acidic than lower, that also we have done. Acidic character decreases down the group. The oxides of E2O of nitrogen and phosphorus are purely acidic. Okay, that of arsenic and antimony are amphoteric in nature, and those of bismuth are predominantly basic. Here we are talking about E2O oxide, but if you talk about this, we have done na, chalo theek hai. Okay, this we have done already. Next is, in case of nitrogen, what will happen? Let us see that. In case of nitrogen, all oxidation state of +1 to +4 tend to disproportionate in acidic solution. For example, you have HNO2 that will disproportionate to HNO3, H2O and NO. Okay, so in case of nitrogen, all oxidation state from +1 to +4 will tend to disproportionate in the acidic solution. Okay, in case of phosphorus, nearly all intermediate oxidation state disproportionate to +5 and -3, both in alkali and acidic. However, +3 oxidation state in case of arsenic, antimony, bismuth becomes increasingly stable with respect to disproportionate. That means nitrogen will undergo disproportionation in the states +1, +2, +3, +4. Nitrogen +1, +2, +3, +4, it will disproportionate, right? Phosphorus, all the intermediate states, right, like +3 we can see, it will disproportionate into +5 and -3, that is also possible. But for antimony, bismuth and arsenic, disproportionation is not possible because +3 oxidation state is quite stable here, right? Then NN bond is weaker than single PP bond. This question also they ask you, why NN bond is weaker than this bond? This is directly your assertion reasoning question or your statement based question. Why it is? Because of high internuclear repulsion. So what exactly? Because the size is smaller, you have lone pair here, so it will cause the repulsion. That is why, because of that repulsion of non-bonding electrons of nitrogen, owing the small bond length, that is why NN bond length is weaker than single PP bond length, okay, because of the repulsion. Next is basicity. As you can see here, that is going to decrease here due to high electronegativity, small size of nitrogen. NH3 exhibit hydrogen bonding in solid as well as liquid state. Because of this, it has higher melting and boiling point than PH3. This is what we did in the chart. We did this in the chart, right? That in the chart we did that why NH3 has more boiling point as compared to PH3, because of the hydrogen bonding here, right? Okay, students. Okay, everybody. Next is reactivity towards halogen. All the trihalides of these elements except those of nitrogen are stable. Okay? Nitrogen are not stable, right? In case of nitrogen, only NF3 is stable. All the NX3 are not stable, but NF3 is stable. All the other trihalides are stable in case of nitrogen family. Is that clear? Okay, right? Understood? Beta, what to teach in this concept? You tell me. Inorganic chemistry, what to teach in this concept? These are factual. These are facts. Okay, these are facts. Should I ask NF3 why you are stable? Right? So only NF3 is that molecule which are going to be stable. And for facts now, you should never, if you want to know the detailed information, click on 20 hours video in one shot. Go through the P block which is taught in around 6 to 7 days in detail. right? If you talk about offline coaching centers, they teach this in around 2 months. P block is taught, not in 1 hour. 1 hour only facts will be taught to you. Have some common sense, right? Common sense is very important for you guys, right? Because you are going to be future engineers. We don't want our roads to be even more worst, right? We already have worst roads, right? So at least use your brain to understand. In 1 hour, the facts can be told to you. But yes, if you give me, ma'am, I have 2 months, ma'am. I have postponed JEE, ma'am. I have postponed JEE, ma'am. I have 2 months, ma'am. I'll taught you P block in detail, right? Okay, so have the common sense, which is very not common in common people. Okay, so as you can see here, some physical properties of group 16 elements. Okay, so these are the physical properties of group 16 elements, atomic radii, all of these things. This is basically the table. So now I'll show you what is the conclusion part of this table, right? This is the table. What is the conclusion part of this table? First is, if you talk about the oxidation state, the stability, we know that the NS2, NP4, this is the oxidation number. This is the electronic configuration. So it can have +6 oxidation state, it can have +4 oxidation state. But oxygen also has -2 oxidation state, decreases down the group, right? But the stability of -2 will decrease down the group. Oxygen will have maximum stability of -2 because of decrease in the electronegativity. Oxygen has maximum electronegativity, that is why it has tendency to accept the electron. Down the group, the tendency will decrease and hence -2 oxidation state will decrease. The tendency or stability of +4 oxidation state in comparison to +3 oxidation state increases down the group. Why? Because +4 is low oxidation state. And always the lower oxidation state, the tendency is going to get increase down the group, right? If you talk about the hydrides here, hydrides are very, very important here. Let us see directly here what you are going to do, right, for the hydrides. So first is the thermal stability. It will decrease down the group. Reducing character, it will increase. So acidic character also, that increases. Bond association enthalpy also, that decreases. This is same as hydrides of nitrogen. Okay, but this is a very, very important exception, that because of this H2O has hydrogen bonding, that is why what should happen, that H2O should have minimum boiling point. But because of the hydrogen bonding, it has the maximum boiling point here, right? Next is acidic strength, increases down the group. As you go down the group, acidic strength is going to increase here, just like your reducing character. But basic strength will decrease. Okay, basic strength is going to decrease down the group. Is that clear to everybody? Is that clear to everybody or not? Now some chemical properties here. But why I can't see any energy, any josh in the chat box, or everything is dull, right? The high amount of energy that I saw yesterday, I think you guys hate inorganic chemistry. Is it? You guys make me feel like that I should not take these sessions because you don't value these things, right? You clearly don't value these things. That is very disheartening to see. Okay. Next we have reactivity with oxygen. All these elements from oxides of EO2 and EO, right? So basically EO2 and EO oxides type, where E, very important. If your E is sulfur, selenium, tellurium or polonium, then only these two are possible. Ozone and sulfur dioxide are gases. Ozone means, if you talk about O3 and SO2, these are gases, while selenium dioxide is a solid, right? This is a solid. This they can ask you which of the following is a solid, right? Reducing property of dioxide decreases from S to T. SO2 is reducing, while TeO2 is oxidizing agent. Again, this is also a very, very, very important property. Okay, this is also a very, very, very important statement, that SO2 is reducing while TeO2 is oxidizing in nature. Besides EO2 type, sulfur, selenium and tellurium also exist in EO3 type of oxides. As I have told you that sulfur, selenium and tellurium also exist in EO3 type of oxides. that is SO3, SCO3, TeO3. Both type of oxides are acidic in nature, right? All the type of oxides are acidic in nature here. Okay, important point is, this was a very important point, that SO2 is reducing while TeO2 is oxidizing in nature. Then O3 and sulfur dioxide are gases, whereas selenium dioxide is a solid. Okay, these two are very important facts from your oxygen family, right? Now let us see some of the exceptions. But we are only talking about the exceptions here. Electron gain enthalpy, because of the compact nature of oxygen atom, very small, it has less negative electron gain enthalpy. Electron gain enthalpy is basically what? 2 when you want to gain the electron, right? So because oxygen already has lone pair repulsion, so that is why it is not very happy in gaining the electron, right? So it has very less negative. That means it does not want to gain the electron than sulfur. However, from sulfur onwards, the value again becomes less negative up to polonium. So that is why electron gain enthalpy order is very important here. That first you have sulfur maximum, then selenium, then tellurium, then polonium, then oxygen. Oxygen does not want to gain the electron because already it has 2 lone pairs. Too much repulsion is there, so it does not want to gain the electron. But a very simple concept is that electron affinity and electron gain enthalpy have opposite sign. Electron affinity is the tendency to gain the electron. If I don't want to gain the electron, I will be negative. If I have negative affinity, ichha, the tendency, the want to have the electron is negative, then my electron gain enthalpy will be on the positive side. That is why this oxygen has negative affinity. It does not want to gain the electron. That is why out of this is on the positive side of the number line. It has positive. As compared to others, it has still less electron gain enthalpy. Okay, it is on the positive side of the number line. Got it or not? Okay. Next we have ionization enthalpy. Elements of this group have lower ionization enthalpy values. Why? Because if you talk about NS2NP4, if they lose, they will become NS2NP3, which is a half-fill stable configuration. That is why to those group 15 in corresponding to period, this is due to the fact that group 15 elements have extra stable half-filled p orbitals. So if it loses one electron, it will gain the extra stability half-filled electronic configuration. That is why it wants to lose the electron. So ionization enthalpy is very low here, right? So this is about the hydride that we just talked about, right? The angle, the boiling point, the thermal stability, acidic basic character, reducing character, all of these things we already talked about, right? Next is towards halogen, how they react. Amongst hexahalides, okay, hexafluorides are only stable halides. Sulfur hexafluorides, SF6, is exceptionally stable for the steric reasons. This so beta, we have also drawn this in chemical bonding, SF6. We have also drawn the structure of SF6 in chemical bonding. So, among these hexahalides, hexafluorides are only stable, and that too SF6 has the maximum stability. It is exceptionally highly stable compound, right? Okay. All the element except for oxygen form dichlorides and dibromides, right? These dihalides formed by sp3 hybridization. If you talk about sp3 hybridization, dihalides means sp3 means they will have basically 2 lone pairs and 2 sigma bonds. Okay? Like you have OF2, right? So you have 2 lone pairs and 2 sigma bonds. These halides formed by sp3 hybridization and thus have tetrahedral structure. The well-known monohalides are dimeric in nature. For example, S2F2, S2Cl2, all these are dimeric. These dimeric halides undergo disproportionation as given below. This is not very important. This they have not asked, so I will not categorize this as very important, but still you should know this, right? Last one is your halogens. So from halogens, they ask too many questions, okay? From electronegativity, electron gain enthalpy, the questions are asked, right? Very, very important. So let us see that. So if we talk about the covalent radii, as you can see, it is increasing down the group. This is also increasing down the group. But if you see the ionization enthalpy, it is decreasing, decreasing, decreasing down the group, right? If you talk about electron gain enthalpy, you will see a very weird trend. Firstly, it is increasing, decreasing, then again it is decreasing. Okay? So, it is very, very important. You should know the trend of electron gain enthalpy here. As you can see, atomic and anionic radii are always increasing, that is right. Ionization enthalpy is decreasing, that is also good. But electron gain enthalpy, you will see that firstly you will have iodine is maximum, then bromine, then fluorine, then chlorine. Down the group, size is increasing, electron gain enthalpy should decrease. It should be fluorine, chlorine, bromine, iodine. But what you will see a switch here, chlorine, and then you will have fluorine. Okay? This is the thing. Chlorine, fluorine, bromine, iodine. Okay? Why? Because why fluorine does not have the minimum electron gain enthalpy? Because fluorine is highly electronegative. Right? That is the reason. Okay? So, electron gain enthalpy is very important. If you talk about the electronegativity order, it is decreasing. Fluorine has 4, that is the highest electronegativity. Melting point, and this is the boiling point. Okay, out of this, electron gain enthalpy is the most important order, right? That is chlorine, then fluorine, then bromine, then iodine. Very, 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 very important. Then bond dissociation enthalpy order is also very important, very important. So what should has happened if you go down the group? You can say that down the group, basically this is F2, Cl2, Br2, then you have I2. So what has happened here? Fluorine has jumped to this position. Okay? You have basically down the group, because the size is increasing, so bond dissociation enthalpy is decreasing. See, size is increasing, that means bond length is increasing. So bond dissociation enthalpy is also decreasing down the group. So the order should have been F2, it is decreasing now, then Cl2, then Br2, then you have I2. This should be the order. But the real order of bond dissociation enthalpy is this fluorine will jump to this side. Why? Again, because of the very small size, right? And also in the small size, ma'am, then so it should be maximum. But it also has 3 lone pairs in the small size. So that is why there is electronic repulsion. That is the reason its bond dissociation enthalpy is less as compared to Cl2 and Br2 because of the electronic repulsions here. Is that clear? These two things are very, very, very important exceptions. Okay, understood? Next is non-metallic character. The non-metallic character decreases down the group, simple. Iodine shows some distant metallic property, right? So it is decreasing down the group. We are saying the non-metallic character is decreasing down the group, right? But iodine shows some distant metallic properties. It possesses metallic luster, forms positive ions like +1, and that means I positive, I3 positive, all of this it forms, right? The negative electron gain enthalpy of fluorine. Now, if you talk about the negative electron gain enthalpy of fluorine is less than that of fluorine, it is due to the small size. This bit I have already taught you, due to the repulsion. This I have taught you here. Why this happened? Because of the 3 lone pair, the electronic repulsions, this happened. Right? This I have already taught you. Next is physical properties. Now let us talk about the physical properties. Physical properties are one curious, very important, one curious anomaly we notice from the smaller enthalpy of dissociation of F2 compound to the Cl2, whereas XX bond dissociation enthalpy from chlorine onward show expected trend, that is this. A reason for this is relatively large electron repulsion. This bit I taught you here. Okay, I have taught you this thing here. This thing I have taught you here. That why F2 has lower bond association enthalpy, again because of the electron repulsions that is written here. Large electron repulsion among the lone pair of F2. Understood? Next we have important reaction things about fluorine. Fluorine oxidizes water to form oxygen, whereas chlorine and bromine react with water to form corresponding hydrohalic and hypohalous acids. The reaction of iodine with water, if you talk about the reaction of iodine with water, is non-spontaneous. That means we have to forcefully do this reaction. In fact, I negative can be oxidized by oxygen in acidic medium, just a reverse of the reaction observed in fluorine. So basically in fluorine, what happens? You have fluorine, what will happen? Oxidizes in water, it will get oxidized to F negative, right? It will get oxidized in water, right? If you have fluorine or bromine, what will happen? Fluorine oxidizes water to oxygen, right? Water is converted to oxygen here in case of fluorine. Whereas chlorine and bromine react with water to form corresponding hydrohalic and hypohalous acid. So if you have chlorine or bromine here in the water, they will form either hypohalous acid or hydrohalic acid. That means these two things it will form. But if you talk about iodine, it will not react. Rather, it will do the reverse reaction. How it will do the reverse reaction? I negative in presence of acidic medium, it itself get oxidized to I2. Itself it will get oxidized. Rather than oxidizing water to O2, it is itself getting oxidizing. The reverse of the reaction is observed. I negative can be oxidized by oxygen in the acidic medium. Is this thing clear to everybody? These three reactions. Most of the reactions of fluorine are exothermic in reaction. It produces a lot of heat. That is why in organic chemistry, we hardly use fluorine anywhere, right? Due to the small and strong bond between them. It forms only one oxo acid while other halogens form a number of oxo acids. Okay? Okay, beta. This thing is clear to everybody. These three reactions. Fluorine oxidizes water to oxygen. Chlorine and bromine, that itself get that will give you in water, it will give you HX or HOX. But iodine will itself get oxidized to I2. Okay? This is reactivity towards hydrogen. Okay? Again, we have halides. Okay? So, halides is also very important. So, it follows the same order as you can see here. They all react with hydrogen to give hydrogen halides. But affinity for hydrogen decreases from fluorine to iodine. Okay? So, the stability, it is going to decrease here. If you talk about the hydrogen halides dissolved in water to form hydrohalonic acid, some of these properties of hydrogen halides are given in table. The acidic character of these varies the order of this. See, this is acidic order. This is acidic or reducing property. Okay? The reverse, if you talk about when HF is greater, then this is the property. This trend is followed by basic character, by thermal stability. This trend is followed by bond association enthalpy. Okay? So these are the orders. So what exactly happens? If you see the melting point here, it is firstly decreasing, then it is increasing, then again it is increasing. So melting points follows an exceptional order here. Can you tell me why? Again, because of the hydrogen bonding in HF. See, what should happen down the group? See, what is the melting point, right? To easily get melt here, if your size is more, right? If the size of iodine, it is more, right? So, what you can observe here, the melting point is maximum. The symmetry is maximum there, right? So, chlorine, bromine and iodine, melting point is decreasing down the group. So, fluorine HF should have minimum melting point, but it is having maximum again due to hydrogen bonding. Similar is in case of boiling point, right? Here you have 293, it is decreasing, then increasing. Why? Again, because of the hydrogen bonding. Melting point and boiling point should increase down the group, but because of the hydrogen bonding and symmetry, if you talk about HF, right? So because of this symmetry, it is having the maximum. Wait a minute, this is less than that, but this is having the maximum boiling point. Okay? Okay, understood? Yes, everybody. Next is bond length, bond dissociation, pK value. That is simply we have done. Because see, if the acidic properties, this is the acidic property that it is decreasing, so pK value will be opposite. That means HF will have the highest pK value, as you can see here. Because pK value is inverse of the acidic character. Understood? Now we have group number 18 elements. Very rarely they ask questions from group number 18 elements. So the important points here to remember is the electronic configuration. The general configuration is Ns to Np6. Ionization enthalpy decreases down the group. Due to stable electronic configuration, they exhibit very high ionization enthalpy. Atomic radius will increase down the group. They have no tendency to accept electron. Therefore, have large positive EGE, electron gain enthalpy values. So there is no as such trend here, but you can see this thing here. Exceptions of noble gases we have is electron gain enthalpy. Firstly, neon, then argon and krypton have same, then xenon, radon, and then you have minimum is for helium. Okay, minimum is for helium. So this is the order of electron gain enthalpy. For physical properties, helium has lowest boiling point of any known substance. It has an unusual property of diffusing through most commonly used laboratory materials such as rubber, glass and plastic. Right? Okay. So beta, this we have done. These are the important, these are periodic. Basically, these are period wise important exceptions. That here you have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Right? Here basically this is the, as we know that down the group size increases, so along the period it will decrease. Right? Here this is out hydrogen and helium. If you talk about, helium has more size, neon has more size, argon. That means if you talk about, if you compare this with the, see, along the period size decreases, but noble gases has the maximum size. Okay, understood? They have the maximum size because see, they are showing van der Waals interactions. That is why they have the maximum size. Okay, this is very, very important. That is the ionization enthalpy. If you see this, it should be lithium, beryllium, boron. Basically, what will happen if you write this here? If you write this in this form only, this would be boron and here you will have beryllium. Okay? If you write this in the same case, this would have been oxygen, this is nitrogen. Can you tell me what is the reason? The reason is the half-filled configuration. Talk about beryllium, it is 1s2, 2s2. That is stable configuration it has. Of 1s2, 2s2, both are fully fit. Nitrogen has 1s2, 2s2, 2p3. This is half filled. Again, it is stable configuration. So from the stable electronic configuration, it is difficult to take out the electrons. That is why it should be that beryllium is more than, so basically we know that it is along the period, ionization enthalpy should increase. It should be lithium, then beryllium, then it should be boron. But beryllium has more as compared to boron because of the stable configuration. Then you have nitrogen and oxygen. So oxygen should have more ionization enthalpy because it is increasing along the period. But nitrogen has more as compared to oxygen because of the stable half-filled configuration. Okay, understood? Because of the stable half-filled configuration here. Next is this also very important. This, I'm just deleting this here. Okay, so it's a very important part, that is ionization enthalpy of 3D series. So what you have to remember, V Coni. What you remember? V Coni. So basically we know that this is 3D. So it should decrease here. It should increase here. So what exactly you are going to do? Saktiv kar man fi koni ku jan. It should be like this. Now, from two things, that is before V before ko, before ni. You just erase this and change the sign. That will be the opposite order. I am just telling you how to remember this. Okay, how to remember this, beta? Firstly, we know that along the period, the size increase, the ionization enthalpy that increases. So write it 1, 2, increasing, 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 increasing. Now in front of V coni, V coni, in front of V coni, change the sign, reverse the sign. So V, this is co, this is ni. Now you have reversed the sign. This will become your ionization enthalpy of 3D series. Is that clear? Okay. Now, next is electron affinity along the period only I am discussing, because you don't have S block right now. So you have to do only this much of the period. So this is lithium, beryllium, boron, electron affinity. Why? Why beryllium does not want to gain the electron? Because it is in the stable electronic configuration of 1s2, 2s2. That is why this becomes the order. Then when you talk about sodium, magnesium, aluminium, right? Magnesium has less as compared to aluminium, again because of the fully filled orbital, fully filled ns2 orbital, fully filled outer s orbital. With this also is clear. Now neon, if you talk about this thing here, it is neon. This is thoda sa weird. Neon, then you have nitrogen, beryllium, lithium, carbon, oxygen, fluorine. This is a very, very, very weird order, but you have to remember it as it is. Okay? My apologies, but you have to remember this as it is. Okay? Is pe to I have already told you, but there are so many complications in this. It is not at all in a regular order. So it is very complicated. So you have to make some mnemonic and remember this. Right? Though it has not been asked, these two things have been asked. This till now has not been asked. But still you should know this. Right? You never know with them. Now, beta, we have completed P block. We have completed the exception of coordination chemistry. Now, the last part is the exception of D block. Okay? Yes, P block exceptions we have completed. Okay? Okay, now we have DNF block exceptions. Let us see that. Yes, do like the video, share this among your friends, because too much hard work we are doing for you, right? Just for you, right? Okay. Now, beta, we have DNF block. So for DNF block, there are some important things here, right? I have taken not too many pages here. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 pages. We know that D block is a very, very big chapter, but P block was also very big chapter. So I am taking out only the important exceptional points here. First is the physical properties. If you see this, you don't have to remember this thing. Just remember nearly all the transition elements display typically metallic properties such as high tensile strength, ductility, all these things, with the exception of zinc, cadmium, mercury and manganese. Zinc, cadmium, mercury and manganese, they have one or more typical metallic structure at normal temperature. Okay, zinc, cadmium, mercury and manganese, right? Except for this, all the other have metallic structure. These does not have any metallic structure. That is the exception. These are some of the very, very important electronic configurations, right? That they usually, that will be very, very useful for you. Most important is this PD, then chromium, copper, this one. All of them are very important, but these are must do. Okay, these are must do. These are some of the things that you must do, that you should not skip here. So I have written all the important electronic configurations here, right? Okay. Next we have is melting and boiling point. So if you see the trend of melting point, if any, so now what they can ask you, the maximum melting point in 3D series, right? The minimum melting point, if you talk about the maximum melting point in 3D series is of chromium, right? The maximum melting point in 4D series is of molybdenum. The maximum melting point in 5D series is of tungsten. So this is something very, very important for you. So mark this important. In any row, the melting point of these firstly rise to maximum except D5 except for anomalous value of Mn and Tc, and fall regularly as the atomic number increases. Okay. So firstly it will increase, then it will start decreasing here. Okay. This one is the exception. It is weirdly very low melting point, and manganese also has low melting point. What should have happened here? It should have increased and then decreased. But now what is happening here? It is decreasing then again increasing because of this weird anomaly of manganese and Tc. Okay, understood? Mn and Tc because of the exceptional behavior. Got it? Understood? This is very important, students. They can, what my idea is, they can easily ask you this question that 3D, 4D and 5D series, what is the maximum melting point? Okay, so that is chromium, molybdenum and tungsten. Okay, next is atomic radii. If you see, atomic radii also is not very good order that it is following. So I have already shown you the 3D series atomic radii there, right? So what is happening? It is decreasing, then it is constant, then again it is increasing, right? Because of the number of electron, DD repulsions, right? Electronic repulsions, this is happening. So basically that is a continuous war between shielding effect, right? So here what is happening? Firstly, it is decreasing till iron it is decreasing, iron, cobalt and nickel it is equal, then again it is increasing. Till here it is decreasing, iron, cobalt and nickel it is constant, then again it is increasing here. Okay, so you only need to remember for 3D series, not for 4D or 5D, you don't need to remember that, right? Next is the higher oxidation state stability. From here beta also they have asked you some questions, some important questions, right? So basically these are the, for halides, what are the oxidation states? So chromium we can say that exists in maximum oxidation states. Then you have vanadium, then titanium and manganese, iron, cobalt, nickel and copper, and then last one is zinc that forms the minimum number of halides here, right? Next is oxidation state. Now I'm going to write some important points of the oxidation states here. That is, oxidation state that is +2 and +4 do occur particularly when they lead to this thing. So it is very important, very important that if you talk about 4f orbitals, right? So lanthanoids are stable in +3 oxidation state. This is a very important point, student. From here you will see a lot of previous year questions, that lanthanoids usually exist in, they have more stable in +3 oxidation state. But what happens is, for cerium, it also exists in Ce+4. For if you talk about europium and Tb, that also exists in +2 and +4 oxidation state because of the half-filled configuration. If you talk about ytterbium, that exists in +2 oxidation state because of the fully filled configuration. These points are very important, that in which oxidation state they have 0, half-filled or fully filled. Mark it, most important. I have a very high intuition that they will ask question from either of these 4 points. Okay, they can ask in this attempt only, because we have observed that in attempt 1 they are asking questions from f orbital lanthanoid, especially the electronic configuration of lanthanoids. So if you see, cerium 4 positive can easily undergo cerium 2 positive, cerium 2 europium 2 positive can easily undergo europium 3 positive. So that is why oxidation number is decreasing. So it is acting as a very good oxidizing agent. This question they have asked so many times. Here oxidation number is decreasing, itself it is undergoing, it is increasing, itself it is undergoing oxidation. So it is a very good reducing agent. It is a very good reducing agent. Okay, so this question also they have asked you so many times. Now if you talk about the oxides here, manganese exists in maximum oxides. If you see, manganese will have maximum number of oxides. The maximum oxide is formed by manganese here. that is Mn7 positive. Okay, understood? That is formed by manganese here, that exists in +7 oxidation state. This question is asked to you. Then apart from these oxides, mixed oxides like Mn2O4, Fe3O4, CO3O4, where these metals can exist in different oxidation states, that are also known, directly aligned from your NCERT. Okay, now this beta we have done already. Okay, this तो I have taught you. This table, this chart we have done. This also we have done. This also we have done. Chal. Now let us see this page. Okay, it's a very important page. Very important page of your NCERT. Let us see this page here. Basically, here the question that is asked from this reaction, okay, and this reaction, okay. So here it is. On the other hand, CO2 positive halides are known except the iodide, okay, except for the iodide, all the CO2 positive halides are known. Potentials are less negative across the and the same. Achha, that is a different page, okay. So on the other hand, CO2 positive halides are known except for iodine. In case CO2 positive oxidizes I to I2 positive. So if you have CO2 positive, that will oxidize I negative to I2. That is not so important. This line is very important. This line. That is, however, many copper 2 positive compounds are unstable in aqueous solution and undergo disproportionation like this. The stability of Cu2 positive aqueous rather than Cu positive. Now this is very important. Very important question can be formed here. Copper is 4s1 3d10. If you talk about Cu positive, it is 3d10. If you talk about Cu2 positive, it is 3d9. But still, why we are saying that here Cu positive, that is 3d10, it is getting dissociated to Cu2 positive. Why? If you see the electronic configuration, Cu positive should be more stable, right? But why this is the opposite? This question has been asked. The stability of CO2 positive rather than CO positive is due to, again, your assertion reasoning question, very important, is due to much more negative hydration enthalpy of CO2 positive, right, than CO positive. So because of the negative hydration enthalpy of CO2 positive, which is more to compensate for the second ionization energy. So if you want to take electron from this stable configuration, you need to have high energy that is provided by the hydration enthalpy of Cu2 positive, right? So the ability of oxygen, that is why this happens. This is a very important thing. Next is the ability of oxygen to stabilize. Higher oxidation state is demonstrated in the oxides. The higher oxidation state in the oxides coincides with the group number attached to the, okay. Now, beyond group number 7, no hydroxides of iron above Fe2O3 are known. So basically, we are talking about this oxide. Okay, this is the oxide that we are talking about. Above iron. See, here you have higher oxides. After this, you don't have any higher oxides. You have +2, +2, +2 oxides. Above iron, you don't have any higher oxides above +2. This is what they are saying here. Okay, this is what they are saying here, right? No higher oxides of iron above Fe2O3 are known, although ferrites are formed in alkaline media, but they readily decompose to Fe2O3 and O2. Besides the oxides, oxocation B5 with O2, basically in +5 oxidation state, right? The ability of oxygen to stabilize the higher oxidation state exceeds that of fluorine. So this question is also asked. Wait a minute. This question they also ask, that is, besides the oxides, oxocation stabilizes vanadium 5 as this ion, vanadium 4 as this ion, titanium 4 as this ion. Okay, why they are stabilizing these things? The ability of oxygen to stabilize these higher oxidation states exceeds that. This question has been asked. That is why I am underlining this thing. the ability of oxygen to stabilize these higher oxidation state exceeds that of fluorine. Oxygen is also stabilizing, but because of oxygen can form multiple bonds, so it can stabilize the higher oxidation state to a greater extent as compared to fluorides. Okay, so exceeds that of fluorine. Thus, the highest Mn fluoride is MnF4, whereas the highest oxide is Mn2O4. So here Mn is in +7 oxidation state. Here Mn is in +4 oxidation state. The reason is very important question. Why fluoride is not able to stabilize higher oxidation state as compared to oxide? Because oxides form multiple bonds, right? The ability to form multiple bonds to make to metals explain its superiority. Okay, this is the answer. In the covalent oxide MnO2, okay? So this is all what is given here. Understood this? Very important point. Okay? Let us see this as well. This to beta same thing we have written here. The unique behavior of copper having a positive E0 value accounts for its inability to liberate H2 from acids. Okay, it is not able to liberate because it does not have a positive, it has a positive plus, it is having plus 0.34 is the reduction potential. So that means it cannot liberate hydrogen from the acids. It is not that strong. Only oxidizing acids like nitric acid, hot concentrated sulfuric acid react with Cu, the acids being reduced. If you want to reduce the acid, you want to gain the H2, right? The high energy to transform Cu to Cu2 positive from Cu to C positive is not balanced by its hydration enthalpy, right? The general trend towards less negative values across this is not important. Just remember that Cu has positive value of E0, right? Okay, from here also I have told you what are the important lines. Then this whole page is very important for you, right? If you actually want to excel in inorganic chemistry, then they are asking questions from this table, right? Which is important. First of all, everything is important here, right? One page I showed you here is this one. This one, I'll just drop it here. Okay, I'll just drop it here. It is very important. Okay, it is very important. Noble gases configuration, half filled. This is the important points from this table. Otherwise, the electronic configuration of this gadolinium is also important, europium, samarium is also important, neodymium is also important, cerium, lanthanum. Okay, all these are very important, right? They have also asked TB. Okay, TB2 positive, TB4 positive, TB4 positive. As you can see, half filled and fully filled. This is half filled. Sorry, this is lanthanide. La3 positive is 0. Cerium 4 positive is 0. Okay. What about half filled? Europium 2 positive is half filled. What else is half filled? Gadolinium 3 positive is half filled. As you can see, gadolinium 3 positive is half filled. Terbium 4 positive is half filled. What about fully filled? Ytterbium 2 positive is fully filled. And lutetium 3 positive is fully filled. So all these that I have circled, these are the electronic configuration. I'll just circle it with red pen, right? So this one, this one, this one, this one, this one, and these two. Okay, that I have circled with red pen. They are very important. Half filled, fully filled, and 0f electron configurations that they will ask you. Very 1, 2, 3, 4, 5, 6, 7. 7 you should remember which element and in which oxidation state. Okay. Yes, is this table clear to everybody or not? Yes, everyone. So 84 minutes. So I think around 1 hour, 25 minutes, and we have completed inorganic chemistry exceptions. From the starting we did, in the starting we started it with coordination chemistry. This page is also very, very important for your VBT theory. Okay, these are the exceptions for the VBT theory. This is very, very important, that will be applied in your exam. Okay, and they will ask you question most probably from the exceptional trends, exceptional lines of the inorganic chemistry. Okay, yes. Okay, start commenting. How can one see your name? Okay, understood. Chal. Okay then students, that's it for today. So on Sunday, what we are going to do? On Sunday, we are going to revise physical chemistry formulas. We are going to revise physical chemistry formulas on Sunday, right, at around 6 p.m. Right, we are going to revise this. I'll send you the link on my Telegram channel. And now for all the students who are looking for very good test series here, so let me show you the test series in this description box only. If you click here, right, if you click here, what you will see, wait a minute, last mile test series, means attempt 2 and English batch, right? So here it is, the test series that you need right now, last mile test series. It is just at rupees 399, and if you want to go for pro test series, that is at 499. Okay, so now here we have extra mile engineering test series, right? If you click here, you will get the extra mile test series 2025, where you will get the test series for around 10 exams like MHT, KCT, Comet K, BitSat, SR, and KIIT. Then you have VIT Triple E. So different state exams and some good university exams. You will get the test series for the best universities that you're going to get here, right? So these test series will be available at Extra Mile Engineering Test Series, and those students who want to prepare for their JEE Advanced, then click on this Eklavya batch. You will get the subscription for the Eklavya batch, where students are getting prepared for the advanced JEE Advanced. Okay, so that's it for today. So on Sunday we are going to do physical chemistry formulas, but I am very, very disappointed to see you guys. I was expecting a lot of students here, right, so that we can do this important stuff with full energy. But I feel so many students watch this recorded. So all those students who are watching this on recorded version, do comment down that how you like this video, and all the students who were there in the live session also, write down in the comments if this benefited you, if this session benefited you in any sense. I would love to know this from you guys. Till then, bye bye, take care. This is Diksha Kaushal.